Welcome to my presentation. I am Greta Tresoldi, Product Manager of LSI Lastem. Today I'm going to talk about the application of the G.Re.T.A system to monitor the integrity of tailings dams. Before, I want to thank Politecnico di Milano and University of Kerman for their scientific support in developing the system. Let me start by giving you some background information. G.Re.T.A is a new geo-resistivimeter designed by LSI Lastem. It is based on electrical resistivity tomography, G.R.T., on the principle that the soil electrical resistivity is function of its hydrogeological parameters, such as water content, presence of voids, or different soil compactions. Unlike the traditional portable systems, it is meant for fixed installation, allowing to monitor over time, in a non-invasive way, the evolution of the underground condition of large sections of soil. Being an energetically autonomous installation, permanently connected to a cloud software, G.Re.T.A can work remotely, while keeping under control the evolution of the resistivity profile of a given soil to assess the variation of water content, the triggering of possible infiltration or possible fractures. From the cloud software, it is possible to visualize and compare the data and set resistivity thresholds that allow G.Re.T.A to be used as an effective automatic early warning system. The system is an off-the-shelf solution, easy to install in a maximum one working day with 2 technicians and does not require a complex configuration that can be done remotely if required. Here there is a short video with the characteristics of the system and some of its applications. G.Re.T.A acronym stands for Geo-Resistivimeter for time-lapse analysis. Here an example of the span of the monitoring system installed on the crest of an earthen dam. This is the system configuration. You can see the solar panel and the modules that compose the system. The measuring part, the power part and the communication part. Nowadays, all the components are included in a single box. The system comes with 2 cables with a total of 48 electrodes. They inject current and measure the voltage to obtain the apparent resistivity map that is then automatically inverted in the cloud software. When subsoil characteristics are changing, the system sends automatically alarm messages. G.Re.T.A can be integrated with all the meteorological sensors from LSI Lastem. Now some examples of the fields of application: monitoring of earthen dams, levees, railways infrastructures, and landslides. The system is very effective also for contaminated sites and landfills. Precision farming is another possible application. The increasing number of tailings dams failures in the recent decades highly demands to set up reliable systems to monitor the stability of these structures. Appropriate design, efficient operation, and continuous monitoring are key solutions to guarantee the stability of earthen embankments, including tailing dams. Electrical resistivity tomography, G.R.T., is widely used in the mining industry for mineral exploration, groundwater studies, characterizing mine wastes, and monitoring acid mine drainage. For these reasons, we present the capability of the G.Re.T.A system for tailings dam monitoring. Since the G.R.T measurement is volumetric and not punctual, the system can monitor large parts of the subsoil. One of the problems related to tailings dams is the accumulation of water in some part of the structure. So this system can be really effective in understanding the processes that undergo the dam body, alongside other more classical measurements, such as piezometric ones. One G.Re.T.A system was installed last August in a tailings dam in Chile during 2 different medium-term monitoring campaigns. Unfortunately, the name and the satellite view of the tailings storage facility can be disclosed respecting the privacy of the owner. G.Re.T.A is based on a well-known geophysical technology, the electrical resistivity tomography (ERT). The method is based on the insertion of an electric field in the ground through input electrodes and the measurement of the voltage in other electrodes. From the measure of the voltage, it is possible to obtain, through the second law of Ohm, the electrical resistivity value that is a peculiar characteristic of all materials. The measured sections need to be processed through the tomographic inversion that, for the G.Re.T.A system, is hosted directly on the cloud software. In this slide, you can see a typical configuration with the solar panel, but the system can also be connected to the electric grid if available. In this case, the frequency of the measurements per day can be higher. Inside the box, there are the different modules: the signal switching unit, the signal driving unit, the main processing unit, the power unit, the battery, and the communication part with a 4G modem router. Unlike the common and multi-purpose portable geo-resistivimeters, the G.Re.T.A system is a standardized solution that can be customized, remaining within two main characteristics: a maximum number of 48 electrodes and a maximum electrode distance of 3 meters. The most common unit electrode spacing are equal to 1, 2, or 3 meters, that allow horizontal length coverage equal to 47, 94, and 141 meters, and the maximum depth of about 7.5, 15, or 22.5 meters, respectively. Cables and electrodes can be stored also vertically inside a borehole. The horizontal installation can be done in two different ways. For a long-term installation, stainless steel plate electrodes are used, since they can be conveniently buried inside a small trench of 40 cm deep that is covered. For temporary installations, stainless steel rod electrodes are handier, since they are inserted in the ground while the cables remain laid down on the soil surface. So, if the user wants to change the position of the profile, it can be easily done. The second type of installation is the vertical one, with two cables inserted in a borehole until a depth of 141 meters. The measured volume is a double cone where the average resistivity around the core is calculated depth by depth. This is the home page of the G.Re.T.A Cloud software, where it is possible to geolocalize the system and to have a first diagnostic, thanks to the traffic light that indicates if technical problems are occurring. Thanks to the platform, it is possible to program the measurements and to see apparent and inverted resistivity maps day by day, since the inversion algorithm runs automatically every time data arrive in the cloud. From the calendar, measurements from different days can be selected and also manually compared. All measurements can be easily exported to other software for further analysis. One strong point of the platform is the possibility of setting thresholds based on percentage of variation in resistivity, and when set thresholds are passed, the system sends automatically alert messages to the defined users. It is possible to insert a calibration curve to correlate resistivity to soil water content. To do so, core samples have to be analyzed in the laboratory to define water content. The calibration can be performed by extracting core samples at different depths, taking the samples to the laboratory, and determine the gravimetric water content along depth. Knowing the resistivity at each depth, it is possible to calibrate a site-dependent function that links the two variables. Between resistivity and water content, there is an inverse proportionality function. Now some slides about the case study of the installation of G.Re.T.A in a tailings dam in Chile. The aim of the monitoring was the localization of the phreatic level downstream two wastewater ponds, the comparison with piezometric data a long time, and the correlation with the variation of the water level in the ponds. The profile 1 is parallel to the underground water flow, while profile 2 is in a way perpendicular to the flow, although topographic variation prevents the exact perpendicular positioning of the profile. The position of the free wells is indicated. Here are some photos of the first profile. The distance between electrodes is 3 meters, with a total profile length of 141 meters and a maximum investigation depth of 22.5 meters. In the side there are 3 installed piezometers, and their position is indicated in the images. In this case, the solar panel option is selected in order to obtain an autonomous installation, since the site is remote. And here some photos of profile 2. Road electrodes are selected in order to move the profile after each medium-term monitoring campaign. 1 measurement per day is programmed. I show only some results from profile 1. Contact resistances are always an issue in arid and harsh environments, such as in tailings dams, even more so since road electrodes were selected in order to move the profile after 2 weeks. Good contact resistances are essential to have good quality data. The first measurement of contact resistances on August 25 shows bad contact on last electrodes, black line. The problem is solved hammering more the electrodes and pouring salt water on the last part of the profile, green line. After 2 weeks, just before moving the profile, contact resistances are good, still around 1 kilo, red line. Every point measurement in an G.Re.T. section is repeated in order to calculate statistics, such as standard deviation of the acquired measurements. Here you can see 2 sections of the standard deviation of the measurements in profile 1. The first, from August 26, has really low standard deviation, indication of good data, except for a line of measurement dependent on last electrodes with higher contact resistance. The second section, measure the last day of the measurements on profile 1, has low standard deviation for all the measurements. Here a resistivity section of profile 1, where it was possible to clearly identify 2 different layers, a top resistive layer until 8–10 meters of depth, and then a conductive layer, less of 80 ohm per meter, that can host the aquifer. In the following slides, we can have an overview of the piezometric data against G.Re.T. measurements along a part of the period of the monitoring, starting from August 26. The position of the piezometer is indicated by the blue arrow. It can be seen that the height of the water table, showed in the histogram day by day, is well identified by the transition between the 2 layers. And then, the variation of the water level, actually not substantial, only 1.5 meter, is followed by changes in the resistivity, with a variation in the position of the border between the 2 layers, going up with the ascent of the groundwater table. During the last measurement, the water table remains the same, and the resistivity data do the same. In conclusion, G.Re.T.A is an innovative geo-resistivimeter meant for fixed installation that is an effective solution for the monitoring of subsoil processes in different fields of application, such as earthen dams and tailing dams, levees and earthen embankments, and contaminated sites. Continuous geoelectrical measurements can indicate the processes and variation in progress in the dam structure caused by seepage, fractures, or different soil water contents. G.Re.T.A is a totally autonomous system, easy to install, and does not require great maintenance. It allows the continuous geoelectrical monitoring over time of large subsoil sections and the effective management of early warnings. The installation on a tailings dam in Chile was successful and provided good data. Contact resistances were tested along the installation period and were maintained low. Standard deviation of the measurements were good, and resistivity data were related to phreatic level near 2 ponds, where observed data through piezometers matched G.Re.T. data. Thank you for your attention. I'm happy to answer any questions you might have. My email address is indicated in the slide.